Right now, at this very second, there is a monster sitting at the center of our galaxy. It has the mass of 4.297 million suns, crushed into a space roughly the size of our solar system. Nothing, not light, not time, not information, can escape it. It is a black hole. And it is 26,000 light-years from Earth. But here's the question that has tortured physicists for decades. What actually happens if you fall in? Let's start from the beginning. A black hole is born when a massive star, typically at least 20 times more massive than our Sun, exhausts its nuclear fuel and collapses under its own gravity. This collapse triggers a supernova, one of the most powerful explosions in the universe, and what's left behind is a gravitational wound in the fabric of space-time. In 1915, Albert Einstein's theory of general relativity predicted that any mass warps the fabric of space and time. Enough mass in a small enough space, and space-time doesn't just bend, it tears. The point of no return around a black hole is called the event horizon. For a black hole with the mass of our Sun, the Schwarzschild radius, that's the radius of the event horizon, would be just 3 kilometers. Our galaxy's own black hole, Sagittarius A star, has an event horizon radius of 12 million kilometers. Not all black holes are created equal. There are 3 main types. Stellar black holes, formed from collapsing stars, typically weigh between 5 and 50 times the mass of our Sun. There are estimated to be millions of them inside the Milky Way alone. Intermediate black holes sit in the middle range, 100 to 100,000 solar masses. We've only directly detected a handful. In 2025, scientists discovered evidence of one via a brilliant cosmic flash that was 100 times brighter than any known supernova. And then, there are supermassive black holes, the cosmic leviathans at the center of nearly every large galaxy. They range from millions to billions of solar masses. The Milky Way's Sagittarius A star weighs 4.297 million suns. The black hole at the center of galaxy M87 is over 1,000 times more massive. Now, here is where things get genuinely terrifying. What happens if you fall in? The answer depends on which kind of black hole, and the counterintuitive truth is this: smaller black holes are far more dangerous near their edge than bigger ones. This is because of what physicists call tidal forces. Imagine falling feet first toward a stellar black hole. The gravitational pull on your feet, which are closer, is significantly stronger than the pull on your head. That difference in force is what rips you apart. This process was memorably named spaghettification, a term popularized by Stephen Hawking. For a stellar black hole, this happens outside the event horizon, visible to a distant observer. Your body would be stretched like cosmic pasta and torn apart before you even crossed the boundary. But here's the twist. For a supermassive black hole like Sagittarius A star, the tidal forces at the event horizon are so gentle that you could cross the event horizon without feeling anything unusual. No pain, no signal, just inside. Only then, as you plummet toward the singularity at the center, over the course of hours or even days in a supermassive giant, would the tidal forces build to their lethal end. Eventually, everything reaches a singularity, a point of infinite density, infinite curvature. Physics itself breaks down. Here's something Einstein predicted in 1915 that still breaks people's brains. The closer you get to a black hole, the slower time passes for you, relative to an observer far away. This is called gravitational time dilation. If you watched an astronaut falling toward the event horizon from a safe distance, you would see them slow down, redden, and apparently freeze at the horizon, never quite crossing it, as their light becomes increasingly redshifted into invisibility. From the astronauts' perspective, they cross the horizon in a perfectly normal, finite time. Nothing special happens at the boundary. They're inside, and they can never communicate that to anyone outside because their signals can't escape either. In 1974, physicist Stephen Hawking made a bombshell discovery. Black holes aren't truly black. They glow, imperceptibly faintly, and they are slowly evaporating. This is called Hawking radiation. It arises from quantum effects near the event horizon, where pairs of particles and antiparticles constantly flicker in and out of existence. Sometimes one falls in while the other escapes. The black hole pays the energy bill and slowly loses mass. How slowly? A stellar black hole with one solar mass would take approximately 10 to the power of 70 years to evaporate. That's a 1 followed by 70 zeros. For reference, the current age of the universe is only about 13.8 billion years, or roughly 10 to the power of 10 years. We're talking an almost incomprehensibly longer time.
But Hawking radiation opened an even deeper crisis. If everything that fell into a black hole is eventually released as featureless thermoradiation, what happens to the information about what fell in? A book, a person, a planet? This is called the black hole information paradox. It sits at the collision point between quantum mechanics, which says information can never be destroyed, and general relativity, which says it can't escape. To this day, it remains one of the deepest unsolved problems in physics. Now, here's where science gets absolutely jaw-dropping. What we've discovered in just the last 2 years has rewritten what we thought we knew about black holes. Record 1, the fastest eater. In 2024, astronomers confirmed a black hole so far away its light took 12 billion years to reach us. It is consuming the equivalent of one entire sun every single day. Its brightness powers the brightest quasar ever detected by humanity. Record 2, the oldest. In 2025, JWST confirmed a black hole designated cfa.LRD-Z9, formed just 500 million years after the Big Bang. It existed when the universe was less than 4% of its current age, far earlier than our models said was possible. Record 3, the biggest flare ever seen. In 2025, astronomers detected a flare from a black hole 10 billion light-years away, designated J2245 plus 3743. Its energy output was equivalent to 10 trillion suns, 30 times more powerful than the previous record. It was triggered by a star being torn apart. Record 4, space-time twisted. In December 2025, for the very first time, astronomers actually watched space-time being dragged and twisted by a spinning black hole in real time, confirming a prediction from Einstein's general relativity that had never been directly observed before. So here's where we are. Right at the center of the galaxy you live in, 26,000 light-years away, a 4 million solar mass black hole is quietly warping space, twisting time, and swallowing the occasional star.
And that's just our backyard. Anyways, I'll be ending this here with this note. Somewhere else in the universe, a black hole is eating a sun every single day. Somewhere, the oldest known black hole, older than our solar system by 9 billion years, still exists. And yet, the most fundamental question, what actually happens to information that falls in, remains unanswered. Hawking died in 2018 without a resolution. The brightest minds alive are still working on it. Black holes are not just objects. They're the universe's hard limits. The places where our best physics runs out of road. And the more we find out about them, the stranger they get. If you want to go deeper on any of this, the information paradox, quantum gravity, or what happened in the first second of the Big Bang, let me know in the comments. Subscribe, and I'll see you in the next one.